with log differentiation, it's just a matter of, first step, take the natural log of both sides. All right, and unfortunately, this is one of those situations where if you mess it up, it's usually in the first step, and that almost always requires you to do the whole problem again. All right, so that would be, aside from this step here, I guess this is really the first step, the first meaningful step after this. All right, because that 2x power only applies to the x. It doesn't apply to the 2. So we can't hop the 2x over the log. Right? Can't do that. Right? At least not yet. Right? We'd have to break up the log by the product rule for logs. So we'd write that as ln of 2 plus ln of x to the 2x. Then we can hop over the log with the 2x. But just the appropriate log, the corresponding log. All right. But if you make that adjustment, it actually makes things a little bit easier, because when you go to take the derivative, that ln of 2 is constant, so that's going to go away anyway. All right. So we're looking at ln of y is equal to ln of 2 plus 2x ln of x. All right. So then the differentiation process occurs. All right, so we're going to take the derivative with respect to x of both sides. All right, so we just kind of do that with a little hand waving. But there was a question yesterday of the meaning of d dx, so I figured I'd discuss that real quick. So when you're talking about finding the derivative of anything, we're saying, particularly with respect to x, we're saying d dx of that expression. So that's what we're doing to both sides. We just don't always show that, or at least show the notation. So I'm taking d dx of both sides of the equation, and that means I'm taking the derivative of this function with respect to x. So the question yesterday was, how's that different from dy dx? So if you have d dx of some function y, that's the same as dy dx, just through ordinary multiplication. All right, so that's why we're able to go back and forth with that notation. It's just this is the more flexible notation because it allows for derivative taking, I guess, related to expressions other than just y. All right. But the next step in the process is really just take the derivative of both sides. So we know that ln of y becomes y prime over y. On the right-hand side, the ln of 2, just looking at that ln of 2, ignoring this for now, just the ln of 2, there's no variable there. All right, so we ignore it. The derivative of that is going to go to 0, so it's irrelevant. So the only thing I care about on the right-hand side is the derivative of this expression, which has 2 factors. All right? A product of 2 factors requires us to use the product rule. So first times the derivative of the second plus the second times the derivative of the first. All right? So the first function there is 2x multiplied by the derivative of the second, which is 1 over x, plus my second function, ln of x, times the derivative of the first, which is just a 2. All right. Now, since ultimately my goal is to get y prime alone, because remember y prime, dy dx, they mean the same thing, I would want to multiply both sides by y. All right, so to cancel on the left, leaving me with just a y prime. On the right, I'll clean it up a little bit. We'd have a 2, or just really a 2, because the x's would cancel out, plus 2 ln of x That's what all of this stuff becomes. But then since the y is really 2x to the 2x, right, these two things are the same, I can replace the y with that. And that's my derivative. All right. So, that's definitely a lot trickier than some of the other problems because, well, just because of that first step, the first real step, like I said. All right. But number 6 really isn't that bad in comparison because, again, you take the derivative of both sides after you introduce a natural log. So ln of y is equal to ln of sine of x raised to the x. Now, since it's only sine of x that's being raised to the x, I can hop the exponent. So ln of y is x times the natural log of sine of x. I don't have to worry about that intermediate step of using a product rule for logs or anything like that. All right. So I still have to use the product rule for derivatives, but that's a different story. All right. So use my trusty highlighter. Going to take the derivative of both sides, so y prime over y is equal to first times the derivative of the second. So shorthand way of just thinking about this is to say whenever you're taking the derivative of a natural log, it's the derivative of whatever is inside the natural log divided by whatever is inside the natural log, right? So the derivative of sine is cosine. And that would be over a sine. So first times the derivative of the second. Now I just need second times the derivative of the first. So plus ln sine of x times the derivative of the first function, which is just a 1. That doesn't bring anything to the party, which is good. So when I go to represent my final answer, all I have to do is remember, multiply both sides by whatever y is. Clean it up if it makes sense to clean it up. Sometimes we, in the last one it made sense because it was just cleaning it up allowed us to write less, so there was a benefit to it, right? And it wasn't difficult to clean it up. Here, the only thing that's going to clean up is that we're just going to get rid of a 1, I guess, all right? But since we know that y is equal to this expression, and these y's cancel out over here, I can now say that y prime is equal to all of this stuff. Okay. Maybe we clean it up a little bit because cosine over sine is cotangent. Less writing, and it's an easy cleanup. Plus the natural log of sine of x times sine of x raised to the x power. All right. And so I'll leave the last one for you to try. All right, nth part, well, the whole function anyway. So f prime of x, tangent has a derivative of secant squared, and cosine has a derivative of negative sine. All right, so we need to find the derivative at pi. So I need secant squared of pi, and this is really minus 9. So minus 9 sine of pi. And you can pop it into a calculator, but if you know your unit circle stuff, then you can figure it out pretty quickly. Either way, you should be able to figure it out pretty quickly. So I'll just put it in the calculator. Because the sine at pi is going to be equal to 0, so that cancels away. And secant is the reciprocal of cosine. At pi is going to be negative 1. Squared is going to be positive 1. But that's a lot of stuff to do very quickly. So just pop it in and go for it. What I would recommend, though, is putting in the original function. So And then do the prime, yeah. So f of x is equal to tangent x, it's a good looking graph, plus 9 cosine of x, even better looking graph, very sassy looking. So f prime of pi is going to equal 1. So all this amounts to a 1. But when you write the equation of the tangent line, it says write or find the tangent line, implies write the equation. So y equals m times x minus x sub 1 plus y sub 1. So we have the m, we have the x sub 1, we just need the y sub 1. The way we would get that is by evaluating the original function. So I would take f and evaluate it for when x is equal to pi. And that gives you a negative 9. So f of pi is equal to negative 9. And so that must be my y1 value. So minus 9.
Wait. But the f of pi on the left is equal to 1. Or the f prime of pi.
Right.
Oh, so then that's the f of pi. Okay.
Right.
I get that.
Fix the m there.
Number 4 on page 20.
Number 4 on page 20.
Mr. Campbell, please go back.
Okay, yeah. So just do it?
No, I just
Oh, okay.